In this tutorial, we're going to be looking at vectors. The tutorial is going to be in 3 parts. This is the first part. There will be second and the third part. For this tutorial, we're going to be covering the definitions, the addition and subtractions of vectors, the scalar multiplication and the multiplication, the unit vector, the zero vector, and a whole lot of others. We also look at the parallelogram law, triangle law, and the polygon laws of vectors. Towards the end of this class, we're going to start by looking at the vectors in 2 and 3 components, and lastly we will look at the laws of vector algebra. Let's get started. We are going to start this class by taking a comprehensive look at the meaning of scalars and vectors. There are two types of physical quantities. The first one, those that have only magnitude, and those that have both magnitude and direction. So physical quantities that have only magnitude are called scalars, while those that have both magnitude and direction are called vectors. So we say that physical quantities that have only magnitude are called scalars, and those that have both magnitude and direction are called vectors. So examples of scalars are length, area, volume, mass, work, energy, distance, speed, and density, while examples of vectors are displacement, velocity, acceleration, force, and momentum. So we have seen that there are two types of vectors, or there are two types of physical quantities, the scalar quantities and vector quantities. And we have seen that scalar quantities have only magnitude, while vector quantities have both magnitude and direction. But one thing we should note is that vectors may not necessarily have any particular position associated with them. So we can have vectors that does not have any position that they are occupying. So such vectors are called free vectors. Such vectors they are called free vectors. Free vectors. So these are vectors that also have any particular position associated with them. So vectors which have particular position associated with them may be located along a straight line or through a particular point. Let's consider an illustration. So we are going to clean this off. So if you talk about vectors, you talk about scalars, examples of scalars and examples of vectors. If you talk about free vectors, so let's talk about the other part of free vectors, which is like the opposite of free vectors. So let's take, for example, a town B which is 100 km north of town A, where B is not 45 degrees east of A. So now I have two towns now, town A and town B. The distance between them is 100 degrees. It's 100 kilometers. Sorry for that. It's 100 kilometers, and we are given that town B is not 45 degrees east of A. So how do we represent this, and how do we show that it does not have a particular position, but it's along a line? So let's draw out our cardinal point first. So you have our north, east, west, and south. So if you are to represent north, 45 degrees east is going to come in this direction. This is north 45 degrees east. But I'm going to clean this out so I will have a larger workspace. So let's have my town here. This is north, this is east, and this is north 45 degrees east. That's the line in between north and east. And we have my 45 degrees here. So we are given that B is not 45 degrees east of A. So therefore, I have my A here and I have my B here. Where this is the north, so this is the east, this is the west, and this is the south. And the vector is represented by this arrow. So the arrow goes from A to B. So the vector 100 km from A in direction north 45 degrees east can be represented by the line segment AB. So this line AB shows the vector between town A and town B. So in this respect, a vector can be regarded as a directed line segment. You can see that vector can be regarded as this. If you have a line like this, A, B, with this direction, this can represent a vector. If you have a line like this. This is A and this is B, and we're given that this goes in this direction. This can be represented as a vector also. So these are vectors that are represented with a line segment. Now let's look at vector notations. So now how do we represent vectors? How do we represent vectors? There's been a lot of representations of vectors, whether in printed materials or handwritten materials. Majorly in handwritten materials, or let's take for example first in printed materials, vectors are represented with bold letters. So if you have ordinary A as this, vector A can be written as this. Oh, sorry, that's too bold. Can be written as this. So if you have ordinary A as this, we can have vector A to be written as this. So this vector and this ordinary scalar quantity. So this is how the first part of how we can represent a vector. The other way of representing vector is the use of caps. If this is A, vector A can be represented with capital letter. And also there's this use of using bar. So people use bar just like an arrow here, like vector A, and also there can be a representation of vector like this with an underneath bar. So it's common to use underneath bar, but most of the time you are going to be using vector written as, let's say vector AB can be written as this. So it means A goes to B, like vector A to B, like what you have been representing the other time concerning line segment. This is AB and this arrow pointing from A to B. To represent this vector, we can use the notation A, B, showing that the vector moved from A to B. Along the line, we are going to be seeing that vector AB is not the same as AB. You can see that the first arrow is pointing forward while this is pointing backward. So there are differences between these two vectors. One is just the opposite of the other. We are going to be seeing this as we proceed. The magnitude of a vector is also known as the modulus of the vector. You can term the magnitude of a vector as the total effect of a vector, and it's represented as this, having two strokes. So if you have vector A, then the magnitude of vector A can be written as this. So you have vector A and the magnitude of vector A. So this is how we can represent. Whenever you see something like this, it means the magnitude of a particular vector. We are going to be seeing how we can apply the magnitude and how we can calculate the magnitude of vectors in coming lessons. Zero vector is a vector with magnitude of 0. So that's the meaning of zero vector. These are the vectors whereby the magnitude is 0, and it's also called null vector. So you might be saying this often. So zero vector are also called null vectors. The unit vector in the direction of the vector A is a vector represented by A and is such that A equal to determinant of A times A. So what does this mean? What does a unit vector mean? They say that the unit vector in the direction of the vector A is a vector represented by what you can see here. A equal to determinant of A, or the modulus, as we said the other time, or the magnitude of vector A multiplied by A. Now let's come back here. We have 2 equal to 1 times 2. You are correct with this. We have 3 equal to 1 times 3. So in this case also, if you have A equal to 1 times A, we are correct. So we have A also. Therefore, if you have A equal to the modulus of A times A, so therefore it now leaves us that for unit vector, the modulus of the vector A must be equal to 1. So this is what unit vector means. It means that the magnitude of a vector A equals to 1. So that is called a unit vector. If you have unit vector of vector A, then unit vector of vector A will be called a unit vector whenever the magnitude of vector A equal to 1. So if the magnitude of vector B equal to 1, therefore vector B is a unit vector. So that's the meaning of unit vector. The negative vector. Initially, we can say that we said AB is not the same as AB. So from here we can point out that this arrow is facing forward while this arrow is facing backward. If we use line segment to represent this, we have vector A, B, and the line goes like this. So we have the vector as A, B. So if you are coming downward, we're going to have something like this, and that's now going to be vector BA. Vector BA in this direction. Vector BA in this direction, meaning vector goes from B to A. So how do we now represent this if you don't want to use BA? So what you can do is to introduce negative, and this is vector AB. So the negative vector of vector AB equal to negative AB. And what is negative AB? Negative AB will be the vector BA. You get that? The negative vector of vector AB is negative AB, and negative AB will be the vector BA. We can see that AB goes in this direction and BA comes in this direction. So if you have AB, which is positive AB, negative AB will be coming downward. This is negative AB, and which is the same as BA. Let's say, for example, if you have a car moving forward, this is C, this is A, and this is B. So this is going from C to A, this is CA, and coming down from C to B, this is CB. But also coming downward like this, we can represent this as minus CA. So therefore CB equal to minus CA. CB equal to minus CA. We can see that the vector CB is pointing downward and the vector minus CA is also pointing downward. Therefore they are the same in magnitude, in direction. So vector CB equal to negative CA. Equality of vectors. Two vectors are said to be equal if they have the same magnitude and same direction. Take note of that. Two vectors are said to be equal if they have the same magnitude and the same direction. So if you have vectors that have this in common, we can say that the two vectors are equal vectors. Now let's get into main business by looking at the addition and subtraction of vectors. The addition and subtraction of vectors. To demonstrate this, let's consider this triangle. We are going to be starting with this. You have a triangle here. Oh, I think I should do that again. I have A, I have B here, and I have C here. Now the question before us is traveling from point A to point C. The task before us now is to journey from point A to point C. There are two ways of achieving this task. Either by going from A to B, then from B to C, or we go directly from A to C. I repeat, I take that again. In going from A to C, so vector A to C can be achieved by going from A to B, then B to C. So by traveling in this direction, we have been able to successfully travel from A to C. If we represent it like we are going from A to B, then B to C. So we have traveled from A, then to point C. Or the other means is to go directly from A to C. We can go directly from this direction, from A directly to C. So if vector AC is set to D, we can see that here that vector AC is said to be the addition of AB plus BC. As you can see that in going from A to C, it passed through AB, then BC. So we can say that vector AC equal to, vector AC is this vector here, AC, this is AB, and this is BC. So you have that vector AC equal to vector AB, which is this vector, plus vector BC. It's simply a matter of direction. If we want to go from A to C, we can go from A to B, then B to C. That's how you have that vector AC equal to the journey from A to B, this is here, and the journey from B to C. This is what we have here. So if we say that vector AB equal to A and vector BC equal to B, so we can say that vector AC equal to A plus B. So we label this as A and label this as B. We now have that vector AC equal to A plus B. So the law that states that, the law that governs this theorem is called the triangle law of addition. Let me write that here. The triangle law of addition. So this is the law that governs the principle that AC equal to AB plus BC. So let's consider subtraction of vectors. So this is simply how addition of vector looks like. You can try more example on complex problems on how to solve the addition of vectors. But now let's look at the subtraction of vectors. So to demonstrate the subtraction of vectors, let's take a look at another triangle. We have been working with triangle quite a lot from the beginning of this class. And let's just introduce the last one before we move into the multiplication and some examples of addition and subtraction of vectors. But before that, let's continue with our triangle. So you have this triangle, here is labeled P. Don't forget we are trying to illustrate the concept of subtraction of vector. This is position R, this is position Q, and this is position S. We have that these two are equal. Now from this, from what we look at in negative vector, we know that vector QS, where's our QS? This is QS, must be equal to negative QR. So this is QS coming in this direction, and this is QR going in the opposite direction to QS. So to make QR comes down, we're going to make it negative QR, which is the same thing as RS. So this is QR going up. If you want QR to come down, it will be negative QR. Then it's now pointing in the same direction as QS, making them to be the same. So if you have that PQ, vector PQ, this is P and this is Q, minus vector QR. This is Q, this is R. PQ minus QR. So we can see that this one equal to PQ plus negative QR. PQ plus negative QR. Now, initially we have that PQ minus QR. This is PQ. And we have negative QR. This is QR. So negative QR is going to be RQ. Therefore, this whole vector is represented as a downward arrow. PQ minus QR. This is what we have here. PQ minus QR. So to change this for us to be able to work with, let's introduce the concept of negative. So here I'm still writing the same thing by saying that this is QR. I'm still writing the same thing. We have PQ plus, then we put the minus QR in brackets. That is plus into brackets minus QR. So we have that PQ plus. Now we have negative QR. Let's take a look at this diagram very well. We have negative QR. These are QR going up, as mentioned earlier. These are QR going up. And negative QR will be going downward automatically. Negative QR will be going downward. Is there any other vector that goes downward here? That is vector QS. Now we can introduce that negative QR equals to QS. Negative QR equals to QS. Therefore, we can come back here and say this is PQ plus QS. PQ plus PQS. PQ plus QS. And this is our PQ already. And let me change the marker type. So this is our PQ and this is QS. This is PQ and this is QS. QS comes downward and PQ goes far into the right. QS comes downward. So we have to add this now, PQ plus QS. From the previous example on addition of vector, we saw that if you are going from P to S, you can travel from P to Q and then from Q to S. Addition here is to go reach point S, and we are starting from point Q. So you can go directly to S, or we go first to QS and then from PQ and then to QS. So we can achieve a movement from PS like that. Therefore, we can have that this equal to PS. This equals to PS. We move first from P to Q and then from Q to S. That is QS. So let's just take a brief example. Let me rub this off. So if you have that from this triangle, that's PQ equal to A, QR equal to B, and QS equal to negative B. So how do we find PR? Let's look at this together. How do we find PR? This is PR from P to R. Along the line, we can see PQ and we can see QR. We can see PQ and QR. And from what we are given here, we are already given PQ and QR. Therefore, we can say that PR equals to PQ plus QR. So this is PR equal to PQ plus QR. This is the first part. So the second part is to find PS. And lastly, we have to look for PS. Actually, we have PS here. This is PS. So let's just put that down. We have our PS is, we are going from P to S. So we can travel from P to Q, then Q to S. So we are going to have PS equal to PQ plus QS. PQ plus QS, or you can say equal to PQ minus QR. I hope you know this why it's the same thing, because this is QR minus QR will be coming down, and which is the same thing as QS. So that's that for addition and subtraction of vectors. Let's look at some numerical examples. After looking at the addition and subtraction of vectors, the next thing we have to look at is the parallelogram law. The parallelogram law. But before we continue, I would like us to conceptualize the meaning of parallelogram law and where we can use it. Let's take, for example, you have a load here. So this load is to be pushed by two individuals. Let's say the load is of 1000 Newton, and the load is to be pushed by two individuals. So let's say an individual, two ropes are attached to this load at this point and at this point. So the first individual pull the rope in this direction, and the second individual pull the rope in this direction. So the vector applied there is a force. Let's say the first individual labeled A and second individual labeled B applied a force of 100 Newton here, and this individual applied the force of 500 Newton. And these two individuals, they are trying to push or trying to pull this load. So how do we conceptualize this? How do we find the resultant, the total force that is being exerted by these two individuals? So at the end of the day, when these two individuals try to pull this load, we find out that the load will move. Let me write this. We move in this direction. And whatever force which is the magnitude of this direction, this will be the resultant. That means the effective force that is actually pulling this load. Individual A applied the force in this direction, and individual A applied the force in this direction. So the effective force pulling this load will be the resultant of the two forces. So how do we calculate the resultant of this? Is then where we are going to be applying the parallelogram law. So let's try to turn this into a parallelogram. This is coming from the root to the head. This is from the root to the head. So if this goes up, I'm trying to draw a parallelogram, and this also goes up. So we have a parallelogram here. Let me clean this off. So whatever the length of the diagonal is, these are resultant. So whatever the length of the diagonal is, that will be the resultant. So now let's generalize the parallelogram law. Let's clean this off and draw a parallelogram. I'll just put that in. So if you have a parallelogram here, this is side A, this is side B, this is C, and this is D. So parallelogram law of vector addition states that the resultant of two vectors is represented by the diagonal of the parallelogram, whose adjacent sides are the two vectors. So if you have side CA to be our first vector and side CD to be the second vector, we label this as A and we label this as B. Therefore, the diagonal of this parallelogram will be the resultant, which is the effective force applied. So how can we use vectors to denote this? Coming back from addition of vectors, if you have CA plus CD, this is CA and this is CD. It's also the same as CD plus DB. Don't forget that in parallelogram, the opposite sides are equal. So CA will be the same thing as DB. And recall that if you have CA plus DB, this is the same thing as CB. If you have CA, CD plus DB, this is the same thing as CB. So we can say that CD plus DB equal to CB. And CB is our resultant. Therefore, the diagonal of the parallelogram will be the resultant of these two forces, vector A and vector B. It's as simple as if you are looking for resultant of two vectors, one in this direction, one in the other direction, and you can bring them to a parallelogram. Just look for the diagonal of the parallelogram, and there you are going to have your resultant, which is the effective of those two forces. Now to talk about the Polygon Law of Vectors. Just like we see from the parallelogram law that they are all coming from the triangle of vectors. The same principle applies to the triangle of vectors, the same principle you apply to the parallelogram law of vector, and the same principle you are going to be applying to Polygon law of vectors. Let's say, for example, if I have something as complicated as this in this direction, let me clean this off. This in this direction, this, and this. So, and we have this point labeled A, B, C, D, E, and F. So let's try to connect all these. A is connected to E, A is also connected to D, A is connected to C also. Recall from the triangle law of vectors that if you have AC, this will be the same as working from A to B and then from B to C. So this will be AB plus BC. So what Polygon law of vector is trying to explain to us is that if you are to calculate AE, which is this length, so we can just work from A to B, B to C, C to D, and D to E. So this will be equal to AB plus BC plus CD plus DE. This will be the value of AE. The same thing applicable if you are looking for AD. So AD will now be what? AB plus BC plus CD. This will be AD. The other ways we can look for AD, we can go from A to C, then C to D. We can also say that AD equal to AC plus CD. So how we come about the second equation was that you're looking for AD, we go through, you're looking for AD, you can go through AC, and from AC to CD. So that is also the same as AD. So this is how we can represent the polygon law of vectors. If you are given a complicated structure, you can just work from the beginning to the end in trying to find the length, just like we find the length of AE. So AB plus BC plus CD plus DE, and that is AE. Now let's start by looking at some real vector operations that you often see around. If you check textbooks, check questions, you often see vectors in terms of I, J, K, or you see X bar, Y bar, or Z bar. Now we are going to start by looking at those ones and how you can manipulate them easily. The topic is actually modulus of vector in terms of components. But before we look at modulus, which is the resultant, we are going to be looking at some basic things. So it might take a little time before we move into modulus. Let's just start with looking at some basics of vectors in terms of their components using the I, J, and K. We are going to start from the Cartesian coordinates, the x and y axis. Then we represent them using I, J, K. We look at operations you can perform with vectors, the addition, subtraction, multiplication, division, and also some other operations. Then we move into modulus of vectors in terms of components. We also will be looking at the direction, cosines, and also the unit vector. Now let's start with the basics. Vectors can be represented in terms of its components by using I, J, and K. Let's explain this. Going back to Cartesian coordinates, the basics one from just the two axes, you have your x-axis and the y-axis. So you can represent a line, a point on this axis. So let's say this is, if this is point 2 and this is point 3. So this point, if this is point A, this is 2, 3. And looking at the third axis, which is the z-axis, so we have our x-axis here, we have our y-axis, and we have the z-axis. So we can also represent points in terms of this component, in terms of this axis, wherever and however we like. So to bring this directly into vectors, we simply denote x-axis with I, y-axis with J, and z-axis with K. X-axis with Y, x-axis with I, y-axis with J, and z-axis with K. But what is the meaning of this, and how can we bring this into the plane? Don't forget that we mentioned that vectors have direction and they have magnitude. So that means if a vector is existing at a plane, we can easily identify it by its direction and its magnitude. So let's say we have a vector at this point. We have the I. Instead of having x and y, we are going to have the I component and the j component. So here we can represent this vector A as 2i plus 3j. So this vector in 2, in I direction and the magnitude in j direction is 3. You understand that? So this vector in x direction, which is the I direction, the magnitude is 2, and in the y direction, which is j direction, the magnitude is 3. This is how we can conceptualize between the Cartesian coordinate of the x and y axis and the vector coordinate of I, j, and k. You can perform operations with this, but before that, let's look at the meaning of column vector. Column vector. So let's say, for example, if you have vector r, if r, this is very simple, let's just start with, if r is represented as xi plus yj. So here I'm using x and y to denote the magnitude and I and j to denote the direction. So I'm here to represent this vector in terms of a column vector. So this is going to be r equal to a long bracket, something like you want to draw the bracket for matrix. So in I direction, what is the magnitude? X, and in j direction, the magnitude is y. So this is referred to as the column vector. So you have represented this in column vector. If you are going to use a normal number, if you have vector r to be 2i plus 3j, I've been using 2 and 3j since maybe I like the numbers 2 and 3. And they are consecutive whole numbers 2, 3, 4, 5, 6. So let me just use 2 and 3. Or should I change to 1? No. I've just used 2 and 3. And we are to represent this in column vector. This is going to be r 2, 3. And that is how we can represent vectors in column vector. So let's look at some operations: addition, subtraction, multiplication, and division. As I mentioned earlier, operations like addition, subtraction, and multiplication can be easily performed when we represent vector in its component. So let's look at these two vectors: addition, subtraction, and it's not actually multiplication, this is scalar multiplication. We're going to be looking at the meaning of scalar multiplication. Let's see. Oh wow. Addition, subtraction, and scalar multiplication. So let's look at two vectors. If you have vector r1, or should I use a and b? No. Vector r1, this is ai plus bj, and vector r2, this is xi plus yj. So you have two vectors there, r1 and r2. r1 is ai plus bj. Recall that a and b, they are the magnitude, yi and j are the direction, and also for r2, which is xi plus yj, x and y are the magnitude, yi and j are the direction. So to perform addition operation, which is r1 plus r2. So to perform addition operation, we are going to add the magnitude that are in the same direction. I don't know if you get that. The magnitude that are in the same direction. So you add the I component with the I component and the j component with the j component. It's very simple. Adding the I and j component together, adding the I and the other I of the other vector, j plus the j of the other vector. So to answer this question now, r1 plus r2 will be, initially let me just write it like this: ai plus xi. That's the first part, that's the I direction, and the j direction is bj plus yj. To better simplify this, we can just simply put a plus x I plus b plus y j. So this is the result of this r1 plus r2. Don't forget, you can't add I and j. You can only add I and I, j and j. So the same thing applicable to subtraction. If you have r1 minus r2, this is going to be a minus x I plus b minus y j. So this is the first one, this is the second operation, and the third operation, which is the scalar multiplication. Don't forget, this is the addition, this subtraction. Now the scalar multiplication. What is the meaning of scalar multiplication? Scalar multiplication is simply the multiplication of a vector by a scalar. If you have vector r multiplied by a scalar defined by k, this is going to be rk. So how do we bring this here? If we choose a scalar number which is 2, let's say 2 multiplied by r1. So if you're multiplying a vector by a scalar, the scalar will be able to multiply the vectors in both directions. That means in the I and the j direction. So this is going to be 2 multiplied by ai plus bj. So here we can just distribute our 2. We have 2 ai plus 2 bj. So this is how we can express the multiplication of a scalar by a vector. Now let's go back to modulus. Now back to modulus. As I said, the modulus is also the same as the magnitude. That means the modulus of the vector is also the same as the magnitude of the vector, and it's represented as bar r. So if you have a vector r, then the modulus is represented as r in is this slash? Is represented with this. So that's how we represent the modulus of a vector. So how do we define the modulus of a vector? Let's consider r again. Let's say r is xi plus yj. And if you have to look for the modulus of r, this is going to be the square root. Take note of this very well. The square root of xi squared plus yj squared. Take note of this formula. We are going to be looking at how we come about this. So the modulus of a vector is represented as the square root of the x component squared plus the y component squared, the I and the j component squared. But before we proceed, we should note that I multiplied by I, this is I squared, and this equals to 1. So I squared equals to 1. Same thing, j squared equals to 1, and also k squared equals to 1. We have not looked at k, but we will be looking at k very soon. So I squared equals to 1, j squared equals to 1, and k squared equals to 1. So we can reduce this formula to be the square root of x squared plus y squared, since both I squared and j squared are 1. So that's how we represent the modulus of a vector. Now let's look at an example. So if you are given two vectors, f vector r1 equal to 2i plus 4j. Now I'm no longer using 2 and 3, I'm using 2 and 4. And r2 also, let me use minus 2i minus 5j. And to find the modulus of these two vectors, so how do we calculate the modulus of these two vectors? Modulus of r1 will be the root of 2 squared plus 4 squared, and this is equal to root 20. And r2 will be the square root of minus 2 squared plus minus 5 squared, and this is equal to the root of 29. So that is simply how we can look for the modulus of vector. Direction cosines of vector in terms of components. Now we'll be looking at direction cosine of vectors in terms of components. So let's give some theories about direction cosine before we jump into direction cosine fully. The direction cosine of vector refers to the angles the vectors make with the x and the y axis. So if you have vector with a vector r or any other vector, the direction cosines are simply the angles the vector make with the x and the y axis. If a vector r, let's define it as xi plus y1 yj, let me write this down. We found that the direction cosine of vector is the angles a vector makes with the x and y axis. So if a vector r equals to xi plus yj makes an angle of alpha with the x-axis and beta with the y-axis. So we define direction cosine, which is the cos of alpha and the cos of beta. We define cos alpha. Don't forget, alpha is the angle the vector makes with the x-axis, and beta is the angle the vector makes with the y-axis. So cos alpha will be equal to x over the modulus of the vector, and cos beta will be y over the modulus of the vector. So this is how we can express the direction cosine. Cos alpha equal to x component over the modulus of the vector, and beta cos beta equal to y over the modulus of the vector. And this makes sense since b is the angle that y makes with the y-axis, and alpha is the angle that the vector makes with the x-axis. Let's have some examples. So I'll just clean this off. So we have an example here that asks us to find the modulus and so also the direction cosine of some given vectors. To find the modulus and direction cosine of r equal to 2i plus 4j, and the second one is r equal to let me write this. Okay, of r1 minus r2. So where r1 equal to 6i plus 2j, and r2 equal to I minus 4j. So we have to look for the modulus and the direction cosines of these vectors. So the first one is r equal to 2i plus 4j. This is quite simple to do. We have seen something like this before. So to start with, you find the modulus. We have to find the modulus. And the direction cosine. Let me just write that in full. So the modulus of this vector will be the square root of 2 square plus 4 square, and this is the square root of 4 plus 16 is the square root of 20. So that's our modulus. Now the direction cosine will be, you know that cos alpha equal to x over the modulus of r. So therefore alpha will be the cos inverse of x component will be 2 over the root of 20. I don't know if you understand this. I should write it more clearly. I'll just do that more clearly over here. So we have defined our direction cosines earlier, and also cos beta equal to y over the modulus of the vector. So now to find the alpha, which is our angle, you know that direction cosine is what we are looking for. I'll just stop in direction cosine, so there's only for us to look for the angle. So cos alpha equal to x. The x component is 2 in this case, and the modulus is root 20. So if you are asked to look for the angle, you can proceed to look for the angle by doing the cos inverse of 2 over root 2. But if you are looking for only direction cosine, you just stop here. And also for the y component, which is the j component, cos beta will be, here we have 4 as the y component over root 20. So these are the direction cosine for question 1. So let me clean this off and start with question 2. So for question 2, we have to firstly compute the subtraction of vector, then we find our modulus and direction cosine from there. The first thing we have to do is to subtract this. By subtracting r2 from r1, let's just do it directly. r1 minus r2 will be 6 minus 1, this is 5i, and 2 minus 4, that is 6, plus 6j. So 5i plus 6j. So the modulus of this will be 5 square plus 6 square, and this is the root of 61. That is 25 plus 36, To find the direction cosine, cos alpha will be, now the alpha component, which is the x component, is 5 over root 61, and cos beta is 6 over root 61. With that, I'm sure you understand the concept of direction cosine and modulus. Now let's move into the unit vector. Unit vector. At the beginning of this class, we have defined the meaning of unit vector. If you want to learn more about that, you can simply go back to the beginning. We've defined the meaning of unit vector there. Here we are going to be looking at some operations concerning unit vector, and now we can calculate the unit vector. So if you have a vector r, the unit vector of r is defined as this. So this is how we denote the unit vector r, and this on top of it. So this is how we denote unit vector. And finding unit vector is not complex. If you define r as xi plus yj, the unit vector of r, which is r, will be the original vector r over the modulus of vector r. Recall that from direction cosine, how we are taking r, this is really related to direction cosine, but in direction cosine we are taking the x and the y component, and we are looking at two different cosines, the cos alpha and the cos beta. But here we are looking at the vector as a whole, the vector as a whole. So we are going to take the vector, instead of taking the x and the y component like we are doing for direction cosine, we are going to take the whole vector. So now that we have vector r defined as xi plus yj, and we are looking for the direction cosine, so the direction cosine of r will be xi plus yj over the modulus of r. The modulus of r. Most of the time you see this expressed as 1 over the modulus of r into brackets xi plus yj. So to better understand, let's look at some examples actually. Let's look at some examples. Find the unit vector of r1 equal to 2i plus 3j and r2 equal to minus 2i minus 2j. So we have to find the unit vector of r1 equals to 2i plus 3j. Now I'm still using 2 and 3 again. And second one, r2 equals to minus 2i minus 3 minus 2. I'm not using 2. Minus 2. Minus 2i minus 2j. Okay, yes. Minus 2i minus 2j. And the first one is 2i plus 3j. So let's look for the unit vector of these two vectors. So the first thing we have to look for is the modulus. This is the first one. The modulus of r in this case will be, by now I'm sure you have already know this offhand, the modulus of 2i plus 3j, as I've been using them since. So this is root of 11. Sorry, that is not 11, that is 13. That is root of 13. Root of square plus 3 square, that is root of 13. And r, the unit vector of r, will be the vector r over the modulus. So in this case we have the vector r to be 2i plus 3j over the modulus, which is root 13. And as I said earlier, this is usually expressed like 1 over r 1 over 13 bracket 2i plus 3j. So modulus of vector will often be expressed as this, where the resultant will be separated from the vector. And the second one, which is minus 2i minus 2j. So here the modulus of r2 will be minus 2 squared plus minus 2 squared. This is 4 plus 4, this is root of 8. And the unit vector of r2 will be minus 2i minus 2j over root 8. And to represent this in the general term, we have 1 over root 8 brackets, that is too much, minus 2i minus 2j. So this is unit vector. And that is that concerning vectors in 2 dimensions. Now we're going to be going into vectors in 3 dimensions. Here we are not going to be dwelling much here, because everything we are going to be doing here, we have already seen them in two-dimensional vectors. We just talk briefly on each part, the unit vector, the modulus, and direction cosine to express vectors in 3 dimensions. I mentioned earlier that we have not seen k. Here we're going to be using I, j, and k. Recall that in two-dimensional vectors, expressing the vector in the component, we have r equal to xi plus yj. But here, if you have a vector r, this will be represented in 3 components: xi plus yj plus zk. So here you have the I, j, and k. Also, operations can be performed easily with this. If you have r1, let's say r2 equal to ai plus bj plus ck. Just like we see in two-dimensional vectors, if you're adding this, also we add the components that are similar, and we subtract components that are similar. Also, we can do scalar multiplication. Let's just do some quick example. R1 plus R2 in this case will be x plus a. We have seen this earlier. Y plus b, j plus z plus c, k. The same is applicable to subtraction. This will be x minus a, I plus y minus b, j plus z minus c, k. And also the scalar multiplication, if you have 2 multiplied by r1, this will be 2 xi plus 2 yj plus 2 zk. We have seen this earlier when we are looking at vectors in 2 dimensions. So that is simply the operations that we can perform with this. Also is similar to the previous ones: the addition, the subtraction, and the scalar multiplication. Now let's look at the unit vector, the modulus, and the direction cosine. While looking at vectors in 2 dimensions, we studied these 3 topics independently: the unit vector, direction cosine, and the modulus. But here I've just packed them all together since we have already understand the concept behind them. So if you have r to be xi plus yj plus zk, so how do you represent the modulus? The modulus will be represented as this. Also will be the square root of x squared plus y squared plus z squared. It's as simple as that, just the same thing. And the direction cosine will now be in 3 directions: the alpha, beta, and the gamma. So this is modulus. So for direction cosine, we have in this case cos alpha, which is x over the modulus of r, cos beta will be y over the modulus of r, and the last one will now be cos gamma, which is z over the modulus of r. So that is our direction cosines. And the last one, which is the unit vector. The unit vector will be the same thing we have seen: r over the modulus of r. This is the unit vector. So r over the modulus of r. So let's just take a look at 2 examples to bring all this into real practice. Find the modulus, the unit vector, and the direction cosines of 1. R equal to 2i plus 3j, I'm using 3 again, minus 4k. And second one, let me start with r equal to I minus j plus k. So here we have to find the modulus, the unit vector, and direction cosine. So let's start from the first one, which is the modulus. So the modulus of r will be the square root of 2 squared plus 3 squared plus minus 4 squared. So here we have 4 plus 9 plus 16, and this is the square root of 29. So that concerning modulus. Unit vector will be 1 over, I'll just write this straight, 1 over root 29 bracket 2i plus 3j minus 4k. So this is our unit vector. And also for the direction cosines, we have cos alpha will be, our x component is 2 over root 29. The cos beta will be 3 over root 29, and cos gamma will be minus 4 over root 29. So that is that concerning the modulus, the unit vector, and the direction cosines. So I'm going to leave this one for you to practice. So the second one, try and practice it. If you have any problem, feel free to post any issue in the comment section below. But to practice this, make sure you get the right answer. You can feel free to share your answer with me in the comment box below. Thank you. So lastly, to round up this class, we are going to be looking at the laws of vector algebra. So from the beginning of this class to this point, we are going to sum up all the laws that we have looked at, and we are going to be titling them the laws of vector algebra. Now let's get started. Yes, congratulations, you have made it to the end of this tutorial. This is the last part. Kudos, you have tried all the way from the beginning of this class to the end. You still stick around to this point. That is very good. So first one, these are the laws of vector algebra. The first one we are going to be looking at, but before we look at anything, let's define our terms clearly. So let's define P. If P and Q are both vectors. So here we are considering two vectors, P and Q. And also let's join one also, P, Q, and R. Let me just write it. P, Q, and R. So if P, Q, and R are all vectors, let's see the laws that hold true at all time. The first one is the commutative law of vector addition. The commutative law of vector addition. So if you have P plus Q, we have already seen that P and Q are both vectors. This is the same thing as Q plus P, and this term commutative law. Law of vector addition. If you have P plus Q, it's the same as Q plus P. I've just seen this one example. I will not be doing for others. If you have 2i plus 3j, this is vector P, and this is vector Q. Let's say this is I plus j. So if you add P plus Q, this is going to be 3i plus 4j. The same thing if you have Q plus P, it will be 3i plus 4j. So we can see that both P plus Q and Q plus P are the same, and this is the first one, the commutative law of vector addition. This does not hold true for negative, so you can't say that P. Notice that P minus Q is not the same as Q minus P. So this is entirely different. It only holds true for addition. So the second one will be the associative law of vector addition. If you have P plus Q plus R, and we have bracket here, so we can also say this equals to P plus Q plus R, and this is the associative law. This is the associative law of vector addition. Try and check this. If you have P plus Q, don't forget, if you have to solve what is inside the bracket first, in both cases we are going to have the same answer. That's the associative law of vector addition. The third one is the commutative law of vector multiplication. If you have commutative law of scalar multiplication, rather, the commutative law of scalar, we have already seen the meaning of scalar multiplication. If I'm multiplying a vector by a scalar, so let's define our scalar by alpha here. Alpha P. We know that P is a vector. It's the same thing as P alpha, and this is the commutative law of scalar multiplication. This is the commutative law of scalar multiplication. That's the third law. And the fourth law will be the associative law of vector multiplication. Of, what am I saying? Vector of scalar multiplication. If you have alpha and gamma as a vector, if you have alpha, gamma p, so both alpha and gamma in this case are vectors, are scalars, is the same thing as alpha, gamma, p. This is the associative law of scalar multiplication. The associative law of scalar multiplication. The fifth one is a distributive law. This is a distributive law. Here we are going to be looking at vector and scalar. If you have gamma as a scalar, p plus q, this is the same as multiplying both sides by gamma. This is, we have seen this initially, p plus gamma q. So we can distribute gamma to both vectors, and this is the distributive law. So we've considered the right, and we are going to consider the right and the left distributive. So the other part, let me just put this here, 6. This is a distributive law. If you have alpha plus gamma multiplied by p, this is going to be alpha p plus gamma p. So we can distribute p to both scalars, which is alpha and gamma, and it's also distributive law. So these are the first, the right and the left distributive. So that is that concerning this tutorial. We started from looking at the meaning of vectors, the modulus of vectors, the magnitude of vector, vector notations, the zero vector, the unit vector, the negative vector, the quality of vector. We look at the addition and subtraction of vectors. We also look at the triangle of vectors. We look at the parallelogram law of vector. We looked at the polygon law of vector. We look at the modulus of vectors in the component. We've looked at the unit vector. We look at the direction cosines. We also look at all those for three-dimensional vectors. And at the end of the class, we look at the laws of vector algebra. So that is that concerning this tutorial. Now you can lay your hands on different examples, try to read further from textbooks, and you're going to learn more concerning vectors. This is not all that we have to discuss concerning vectors. There's going to be 3 parts for this tutorial. This is the first part, there will be second part and the third part. This is just an introductory level into vectors. In the next tutorial, we're going to be starting with vector part 2. So I will see you then. Don't forget, if you have any question, feel free to drop them in the comment section below. And if you like this video, share it and don't forget to subscribe. Thank you.